let's start. Hola, I'm Michael and I'm from Poland. And I work at a company called Softwaremill. It's rather a small company because we hire around 40 people, but it's unique in two ways. Because first of all, we don't have any office. So everyone works from homes, co-working spaces, etc. And additionally, we've got a fully flat organization structure. So everyone is like a CEO and can make even financial decisions. But today, I would like to talk about machine learning. And let's start with a small quotation. Can machines think? It's a question asked by Alan Turing in 1950, specifically in his scientific paper, in which he considers different challenges which stands before the process of the learning of the machines. And this paper is also a source of a test called Turing test, in which we have some independent judge or interrogator who talks with different people and tries to guess who is a human and who is a machine. And until today, no machine has passed this test yet. So, what is really machine learning? In machine learning, we try to make machines think like us, humans, and to make them able to detect some patterns in data and make decisions based on them. And the second part currently works quite good. If machine has a defined algorithm, way of processing parameters, then machines can process even larger amounts of data than humans. But they still need us. They need us to define this algorithm, way of processing parameters. So fortunately for us, machines won't take over the world today or tomorrow, but nobody knows what may happen next. And there are a few types of machine learning. I will go now through them. And first, we've got big category of supervised learning. And you can imagine that you have some examples, some rows, examples described by attributes. And you want to predict some value for each example. And in supervised learning, you know some original value you can predict, and you can compare if the prediction was correct or not. And in supervised learning, we've got two smaller subgroups. There is classification. If this value you would like to predict is some type of categorical nominal value, then it's a classification. And this can be, for example, classification of emails to one of the categories, or to spam or not spam. And if this output variable is a number, then we have a regression. And this can be, for example, trying to predict stock prices. And then there is another big group, unsupervised learning. And in unsupervised learning, we don't have such output variable, and we are more interested in what is the whole result of the whole algorithm. So in case of clustering, we group similar objects together, but there can be different measures of that similarity. We may group events with similar location, but we may also group people who have some similar interests in social network. And when we have groups, then we can target our marketing campaign to some specific group. And like in this picture, we have some variables grouped by some attributes, by colors, but we don't have really labels, so we don't really know what they are. We only know that they are similar. And another category is dimensionality reduction. And in this one, we just want to reduce number of attributes which describes our examples. So we may have some examples put in a three-dimensional coordinate system, and then we may do some transformations, reduce number of attributes to not lose any important for us info, for example, about those groups, those separate groups, but reduce the complexity. And then next big group is semi-supervised learning. And in this group, we have labels, but not for all the examples. For example, obtaining label might be pricey, might need human time, may be related to some cost. So we have labels only for some small subgroup, but having for only those small subgroup can benefit the whole processing. And reinforcement learning. And in reinforcement learning is easiest to explain basically on games. So in games, there is some initial state, there is some goal, and there is possible state of moves. And when there's some artificial intelligence, it has to decide what moves to take to maximize some function. So if it makes good moves, then it gets good points, and if it reaches the goal, then gets some big reward. If it makes bad moves, then gets some minus points. And this can be also applied to movement of robots, when a robot needs to move between some 2 points, and if it will hit some obstacle or wall, will get just minus points. And I have mentioned here AlphaGo. It's algorithm from Google for the Go game, and based on the DeepMind system, and it was recently able to beat the best human Go master. And it's worth to notice that Go game is much more complicated for machines than chess, and it took many years between those two events. So, there are also other use cases. There is voice recognition with all these assistants like Siri, Cortana, Alexa, etc. Fraud analysis. And here was an idea in Poland from Polish government. They wanted to build a large system which would gather all the possible invoices and then run analysis on it to find all the frauds, etc. Then face detection. So all security reasons related to detecting faces of specific people. And next one is related to ads on websites. And with ads on websites, usually the company who displays ads gets money only when viewer clicks the ad. So it tries to maximize the probability of clicking by profiling the viewer of the website and by matching the best ad for a given person. Spam detection, already mentioned. Shop recommendations. So all recommendations, all emails like from Amazon or eBay that you might be interested in this product, but also basket analysis, like people who buys products A and B also buys product C, for example. Photos descriptions, and there are algorithms for making captions for photos. So you can upload a photo and get description when there's a car, tree, etc. on it. And healthcare, where having a lot of data, it's possible to find the best way of treatment for given patient. And there is some common learning process for the machine learning. And I will focus today mainly on the classification problems, because I will show you in one moment a classification problem and solution. So during learning process, you have to first gather your data. So your data may be located in multiple data sources. They may have different schemas. So you need to bring them to some common schema. And additionally, if you have some categorical attributes, it might be needed to normalize the names of those attributes inside. And when you have gathered your data, then you have to clean it, because some data may be missing some attributes values. There may be some nulls, some empty strings, and you have to decide what do you want with such examples. So you may want to remove such examples, but you may also want to approximate somehow values with some averages, medians, etc. And also on the other side, there may be outliers. And outliers are cases where some attributes have values which you know that for sure are wrong. For example, if you would have some person with age with minus 300 years, then you know that for sure it's wrong. And you have to decide, what do you want? Do you want to remove such example, or do you want to approximate again with some average age, for example? And then you perform the feature engineering. And in feature engineering, basically you create features from existing features. So you may have, for example, field name with a name, surname, some title inside of one field. And you may just want to split it to separate fields, because, for example, this title might be important. You may have some sound file, and depending on what do you want to process, some different sound characteristics may be useful. You may be comparing some texts, and when comparing texts, it might be good to have some additional attributes like length, difference of lengths of both texts, or number of common words, etc. And when you have prepared your data, and some people say that it may take even 80% of the whole learning process, then you have to split your data. And the simplest method is to split it to train and test set. For example, to 3/4 and 1/4 of the size. And then you take this train part, you take some machine learning algorithm, and it learns only on this train part and produces some model. And then you have to verify how good is this model. So you take the test part, you take the model, and check how it reacts to those samples it didn't know before. If it will be, it will manage to predict correctly those values you want or not. So you perform the evaluation, and you may calculate, for example, accuracy, just to get some percentage, how big percent of the samples were correctly classified. And usually in first try, this accuracy is rather bad. So you have to go back to change the cleaning method, to add additional features, to change algorithm parameters, etc. And you go again and again until accuracy is enough for you. And when it is enough, then you have your perfect model, and you can apply new observations to it without having this value you would like to predict. So example. And our example is to classify conference talk abstracts into tracks. So on some conferences, talks are divided into tracks like mobile, backend, front-end, for example. And I have gathered some abstracts from a few conferences. I have normalized the names of the tracks, and I have gathered over 100 such abstracts and put them into the CSV file we will be using today. And we're going to use Apache Spark. And small disclaimer, Spark is generally a big data tool, so you should use it only when you have really big data. So if you can't process your data on single node, when you can't scale more vertically, and you have really to move to cluster processing, then Spark is for you. And Spark, from developer perspective, offers RDDs, which are like distributed collections. So from the developer perspective, they offer a collection like APIs with some map, filters, etc. And underneath, they have data distributed among multiple nodes in a cluster. And if processing on one node fails, because everything can happen, then it knows what part of data needs to be recomputed. It doesn't need to restart the whole processing. And in current versions, RDDs are often hidden underneath other APIs, like data frame. And Spark has some extensions, for example, Spark SQL for support of SQL language, mlib with machine learning algorithms, which we'll be using today, GraphX for graph analysis, Spark streaming with stream processing, and it offers APIs in Scala, Java, Python, and R, but R with some limitations. And we're going to use today Scala. So code of this whole example is on GitHub. There will be also another link to it. And so let's go to the code. And for the coding, I'm using here Apache Zeppelin. And it's a notebook application. And you may have heard about other notebooks like Jupyter, Spark Notebook, IPython, etc. And generally, these are web applications in which you can create such notebook files where you can execute some code, Bash, Python, Scala, Java. You can results of those execution. And these results can be saved inside this notebook. And additionally, they can be visualized. And apart from that, you can mark some, leave some comments, for example, in Markdown. So notebook may contain the whole way of processing with comments, explanation why, and visualized results. So I have here some notebook template, and first cell just contains execution of Bash. To download the abstract CSV file from my GitHub to Docker container, because this Zeppelin instance is running together with Spark in some Docker container. And second cell, just some imports we'll be using today. So let's load our data. So value data equals. And Spark is an entry point for the data frame APIs. And we have to say a few things. So we're going to read file with some options. First, the limiter in my file is a semicolon. And additionally, I have to define that there is a header line with column names. And it's a CSV file named abstracts CSV. And let's see what's inside this file. z.show is a function from Zeppelin, and it should display a small table for us. Okay, so here's the table. And as you can see, this file contains 3 columns. There is label with the name of the track, there is title with the title of the talk, and text with the abstract itself. And you can do some things with this table, for example, to display what is the distribution of the labels. So we have labels like backend here, big data, DevOps, frontend, Java language, methodology architecture, mobile embedded, and programming languages. And now, I haven't told you one thing, that most of the machine learning algorithms require to have numerical input. So you need to have both numerical feature and numerical features and numerical label, this value you would want to predict. So now we have to transform our data to form of the numbers. And we're going to use Spark transformations for that. I will move this a bit so you can see this good. So first let's focus on a label. And we just need to transform this label to a number. And there's transformation for that named string indexer. So new string indexer. And we have to define 2 things. What is the input column name? So it's the label. And what would be the name of the result column after the transformation? So indexed label. And we have to provide here data so it can index all the labels in the data set. And so let's apply this transformation. And now I will apply this transformation step by step to show you how the data changes and what columns are added, etc. But later we're going to build a pipeline where just in one step it will execute everything. So value indexed equals string indexer transform data and z.show indexed. Okay, transform. So we have again our table. Our first example is here generally backend reactive streams principles applied in Akka streams, and we'll be mainly looking for it for a part of this presentation. And we have index label here with value 2.0. And so backend is mapped 2.0, and we can look for some other values. So there's 1.0 for big data. So we have just created some small index. And now I will define also the opposite transformation, because at the end we'll go get also the numerical prediction, and we just need to transform it back to the string label so it's easier for us to read. So this is the transformation index to string with input column will be named prediction, and output column will be prediction label. And we have to define here set labels with string indexer dot labels. I will add an enter so you can see. And we're going to use it later and apply it later. And now, so we have our label already as a number. So now we can focus on the title and text. And first thing is that if you would read this whole data set, you can notice that sometimes some technology name is mentioned only in title and is later not mentioned in the text. So we want to use both of them. So let's just start with concatenation of them. And we're going to use some fancy transformation to show some Spark features. So SQL transformer equals SQL transformer. Sorry. And okay. So if someone was sleeping, it's not already. Okay. So we define here a SQL statement, and it's a select of all existing columns and concatenation of title space text as title and text. So this will be name of the new column from this. So this means that from currently applied data frame. And let's apply it and see the result. So value transformed equals SQL transformer transform indexed and z.show transformed. And we see our example, and there's new column title and text, and it is just concatenated. And now we have concatenated it, but now we want to split, but split to separate words. So another transformation, regex tokenizer, and we define again the input column, which is title and text, and the output column, which will be words. And we have to define pattern, which will be in the regex. And let's say we want to split on all non-word characters. So value words equals regex tokenizer transform transformed and z.show words. Transform again. So there is new column, and we see that there are just words without any special characters. And we can see here that there are some words which might not be useful for us, like in, we will, at, etc. And these are just stop words, so we can filter them out. And there's another transformation for that. So we're going to use stop words remover. So new stop words remover. We define what is the input column, which is words, and what will be the output column, which will be filtered. And we're going to apply it. So value filtered equals stop words remover transform words and z.show filtered. So we see again our table, and there's new column filtered. And in original words, we had reactive streams principles applied in aka streams in this talk. And result is we have reactive streams principles applied. There's no in aka streams talk, so stop words were removed. And now, well, we have already filtered words, but now we have to transform them to numbers. So we could think of solution where we would have, for example, whole English language dictionary. And we could define for each such abstract an enormously large vector in which a single vector position would correspond to a single English language word. And we would put in that vector numbers which would relate to number of occurrences of a given word in a given abstract. But we don't have such dictionary today with us, and it would be very large vectors. And additionally, often technology names are not from English language, so this wouldn't work. So we're going to use a small trick. And this trick is called a hashing trick. And there's transformation for that, named hashing TF. TF from term frequency. And we define what is the input column here, which is filtered, and what is the output column, which will be features. And we have to define one additional thing, which is number of features. And let's say now 2048. And I will say more about that number later. But generally, hashing term frequency takes those words, calculates hashes from them, divides modulo this number, so here 2048. So it's like splitting those words into buckets. And we're defining here a number which is smaller than the dictionary size. So there may be some conflicts. In case of conflicts, it just adds the occurrences, but we won't worry about them now. So let's see what is the result actually. So features equals new hashing TF. Sorry. Hashing TF transform, and there was filtered. And z.show features. And well. Okay. And the thing we have expected to see here was the just vector of length of 2048 with those buckets. But we see something else because Spark is quite clever. And it knows that this transformation may produce something which have a lot of zeros. So it uses another vector representation which is sparse vector, and it contains 3 values. And first value is just a size of the vector. And then there's an array of the indexes and array of values. So basically this means that from index 0 to 38, we had only zeros. And at position 39, we have value 1.0. And then from 40 to 147, we had also only zeros. And at 148, we have value 1.0, etc. So basically, this is another representation of to save the memory usage, to omit all those zeros. So now we have already the numerical label, and we have numerical features. So we can define the machine learning algorithm and perform the learning itself. So we're going to use naive-based algorithm. And this algorithm basically calculates probabilities of occurrences of specific words in specific classes. And it's naive because it naively assumes that those probabilities are independent. And you have to define for it 2 things. What is the label column, which is our indexed label, and what is the features column, which is now features. So, and I want to apply it now. I will construct this pipeline I was mentioning at the beginning. So let's gather all those transformations step by step. So pipeline equals new pipeline with set stages. And we define here an array. And we say that first we had our data, and we have applied the string indexer to transform our labels from text to number. Then we have used a SQL transformer to concatenate title and text. Then there was regex tokenizer to split to separate words, stop words remover to remove the stop words, hashing TF to transform to numbers, then comes in the naive base to perform the learning, and at the end this transformation we were not using so far, which is index to string to transform it back to labels. And now I have to do one more thing, because in the learning process I have mentioned the part of splitting our data. So let's split it to train and test. So we're going to have train data, test data, and we do this by data random split, and we define array 3/4 and 1/4. And we want to produce model. So we take pipeline, we provide to it train data, And with model, we can make predictions. So we want train predictions to see how it behaves for the train data, and test prediction to see how it behaves for this data it didn't knew during the learning. So we have model, transform, train data, and value test predictions is model, transform, test data. And now let's see what are the test predictions and if this works. Okay, so there's set features column. And it's thinking, and there's a table. And we see here different first row because it was random. Our data, maybe I will move for one moment again to code, because it randomly split. So we're seeing here what is now in test. So the row we were looking before at was put in train. So first row in test is backend building multiplayer games using streams, and there's some abstract. And you can see here all those columns we were before applying manually, creating manually by transformations, but here pipeline just applied everything. And we see something new. There is row prediction from the naive base, and there are probabilities from naive base, and there's prediction in form of number and in form of the text. So first row was backend, and is predicted to be also backend, so it worked. Second row was backend, and originally it was also backend, so looks nice. But we won't check step by step all the examples in this set. We are going to use an automatic evaluation. So let's define evaluator. And in this multi-class, because we have multiple possible classes, classification evaluator. And we have to define what columns it needs to compare. So set label column to indexed label, and set prediction column to prediction. And we have to define one more thing, which is the metric name. And let's say we want accuracy. And we take, to get train accuracy, we take the evaluator, evaluate train predictions, and to get the test accuracy, we have evaluator, evaluate test predictions. So we get two numbers. First is 1.0, and this means that this model is able to predict those labels from the train set with 100% accuracy. And this usually means that there's an overfit in this model. And for the test set, it works correctly for 59%. So it's not bad, not good. It can be definitely improved. But about that later. And the last thing I want to show you here in the code is how to apply this model to new observations. So new observations, which is not from our CSV file and doesn't have really this label column. So we define the new observations, which is Spark create data frame, where we have to define sequence of tuples, which is title and text of our talk. So machine learning by example with some, I will present Spark, for example, and let's add something more. There was the Docker patterns, for example. Let's see. And we have to define that this will be the data frame with columns title and text. And let's quickly display how works model for them. So z.show model transform new observations. So our model produced all those columns, and for machine learning by example, it have predicted big data, so it have worked. And for the Docker patterns, it predicted DevOps, so it also is not bad. And now let's go back for a few slides. So what can be improved in the sample? So for sure, our data set could be bigger, because having only 100 over 100 example is not enough, for sure, not enough for Apache Spark. So bigger data set would be useful and could lead to better results. And then there's, hello, test, okay, of tokenization. So this algorithm worked like this. So when we had a sentence, I will present big data topics, it have split it to separate words. So by doing that, we have lost some information, because big data was split to separate words, and big and data doesn't have the same meaning. And this could be also case, for example, for Java EE, where it would be split to separate words or terms. And for example, we could use instead n-grams, where n-grams produces I will present big data topics. So by combining maybe those bigrams with original terms, we could get better results. Another topic is stemming and lemmatization. And English language is quite simple, relating to all the flexible forms. So in this example, it wasn't bad. But Polish is, for example, a bit more complicated. And all flexible forms by this algorithm would be treated as totally different words. But basically, flexible forms should be transformed to some base form. So there is a stemming, for example, Porter's stemmer, which is like a bit of a heuristic, where it just cuts off the different endings, leaving the common beginning for the words. So communities and community, it transforms it to the common. So drawback is that it doesn't sound like the original word, but it can work with such problems. And another case is the lemmatization. And lemmatization actually knows the grammatical rules of the given language, so it can really bring the original base form. Next one, TF and IDF. So we have used here in that hashing TF, which is hashing term frequency. And generally, this means that it increases the importance of those terms which occurred a lot of times in given document, here in given abstract, because we are summing up numbers of occurrences. And there's another thing like IDF, inverse document frequency, which lowers the importance of those terms which occurs in a big number of documents or in big number of abstracts. So if there would be some words typical for abstracts like talk, speak, etc., then their importance might be lowered by IDF. And then we have used here a simple split to 3/4 and 1/4 to train and test, but something more complicated could be used to get better results, which is KFold cross-validation. And for example, for 4 folds, it splits data to 4 parts, and it performs 4 iterations of learning and testing. So each fold is once in test, 3/4 in train in this case. And it calculates the results, accuracies from such learning, and then calculates the average. And this average is much more reliable, also thanks to that each example is at least is once in test. So there are not situations like something was only in train part. And grid search. Because there was this number of features parameter where we have just put 2048, but we don't know if it was the optimal parameter for this processing. So in Spark, you can define array of values you would like to check, and Spark can combine this with cross-validation and find what is the optimal set of parameters, because there can be more parameters with some values to configure. So it checks and produces the best model. And some links and references. So first link is this paper from Turing, which I have mentioned in the beginning. Second link to the documentation of the Apache Spark. Third link is the Databricks site. Databricks is generally a company who offers some supported paid version of Spark, but also they offer some hosting environment where you can create a community account where for free you can run some single node of Spark with some notebook integrated. Fourth link is from Google about making captions for the photos. Next link about the Go and AlphaGo beating those Go master. And next one is Kaggle.com. It's a site with machine learning competitions, and it was recently acquired by Google. And basically, there are private companies who have their problems related to machine learning. They put their problems there. They put some money rewards, and people just compete to produce the best models to solve those problems. For example, there were problems related to counting numbers of sea lions from photos for some environmental companies, or to finding duplicate questions on Quora, or some creating automatical categories for YouTube videos and more. And last link. So Docker Zeppelin is the Docker container as I was using today, which combines just a single node of Spark together with the Zeppelin. Spark Core NLP is an integration of Spark with Stanford Core NLP library. And this library just offers some more advanced NLP features, so natural language processing, so lemmatization, stemming, etc. And last link is the Coursera with a course from with the Spark and that's all for today. I have some stickers if you would like to have some of them, not only those from the slide. Just grab them after the talk. And do you have any questions?
Hi.
Hi.
Thank you for the talk. You've been very brave because coding life is like difficult. My question is, all the examples you show is using plain Scala libraries, or is something that is not Scala but Spark?
This whole example is using those things from Spark. This notebook is connecting to Spark, and there were at the beginning those imports from Spark libraries.
You mentioned that R has some limitations with respect to Spark. Can you mention some of the limitations?
At least, especially in, for example, Spark 1.6, there were some limitations in APIs. There were some methods missing which were available for the rest of the languages. For example, as I remember, there were missing some methods like repartition by key, but it was filled in the Spark 2.0. So it's now better. So I'm not sure if everything is already included in R in 2.0, but it's for sure better.
From all the learning process, which of the steps would you consider is more important? Like, is feature engineering crucial or critical to get better results?
Well, usually yes. Because, for example, in base data, I can tell you, for example, about those problems from Kaggle. There were those competitions with trying to find duplicates between questions. So you had a pair, and it was needed to analyze if this pair of questions asks about the same things. And just having raw text is not enough. So you need to produce things like what is the number of the common words, if the word order of these words matter, if there can be some not exact words similar, some synonyms, for example. So this usually needed to produce more of those features, to produce some cleaned features, sometimes normalized, etc. Okay, if there are not more questions, you can ask them after the talk, and thank you.